Hi, everyone. Welcome to today's webinar. I'm Michaela, and I will be monitoring the chat during our time together. Today's presenter is Oleg Chunikhin, CTO at Kublr. Oleg will be explaining how to pick the right container runtimes and tooling. If you have any questions, please post them in the chat, and Oleg will make sure to address them at the end. Okay, let's go ahead and get started.
Hey, hello. Thank you for the introduction, Michaela, and welcome everyone to our webinar and the presentation. So thank you for joining. My name is Oleg Chunikhin. I'm CTO at Kublr. Has a lot of experience with container and cloud native technologies, and not least because of working on these technologies within Kublr over the last 5 years. So we built together with our team a Kubernetes management platform, a tool that allows companies, enterprises to manage Kubernetes clusters across different environments, across different clouds, on-prem, and provides a set of essential operational tooling around Kubernetes. So, this webinar continues a series of webinars that we created for explaining both basic and advanced topics in cloud native world, essentially, because what we see in our implementation projects, in our clients' projects, is that having great tools for Kubernetes management and container orchestration is probably only half of the deal when you're implementing cloud native architecture in your environments. Another half is actually learning this ecosystem concepts behind the ecosystem, and one of the foundational concepts in this world is containers, container runtimes, and container management. And this presentation and this demo is going to talk exactly about that. So, and this is not a simple topic, albeit being foundational element of the ecosystem. Historically, containers, container management took quite a complicated path. So if we see how the technology was developed, we can look back 9 years already. In March 2013, Docker released its first open source product for container management, and at that time it used Linux LXC for container management. Later, Docker separated container management and switched to a different library or different approach to managing containers, implementing this container management logic completely from scratch in Go, and made libcontainer part of the product. Further, we can see that in 2015, standardization effort was formally established. OCI was created by Docker, Koros, Google, Microsoft, and many other companies. And OCI is essentially a specification, a standard describing how containers should work and interoperate. And we'll talk about that in a few minutes. Now, in 2015, also container orchestration with Kubernetes started when Kubernetes 1.0 was released as an open source product. in 2016, Kubernetes 1.5 at that time introduced another specification called CRI. And we'll talk about that in a few minutes as well. And then Docker, at that time, Docker was probably the main and the only, the most commonly used container management and container management tool. So at that time, Docker split the project into several pieces, separated Moby as an open source upstream development, essentially branch for Docker and the basis for commercial products, Docker Enterprise Edition and Community Edition, Docker CE. Another specification and the implementation of container management tools was introduced by Red Hat in 2017, called CRI-O. Then we see development of OCI specification, and it was expanded in 2018. Container distribution Docker registry specification was added to it. And last year ago, OCI distribution spec reaches 1.0. And we now in so now we have more or less mature standardized field which is populated with a number of tools, specifications, and relatively well interoperable technologies. And this is what we are going to look into today. So because of this history, unlike some other technologies, let's say if we are looking at cloud technologies, and we could take a look at two major vendors like AWS and Azure, those are very comparable things. They have different implementations, that they have similar concept behind them. So with containers, tools populating this field may be really confusing, because when we are talking about things like containerd and Docker, for example, we are not talking about different implementations of the same specification. They have much more complex relationship. Let's say, just for example, containerd is a part of Docker, but at the same time, containerd can be used separately from Docker and for the same purpose as Docker is used as a part of Kubernetes, for example. Moreover, Kubernetes, while initially using Docker as a container runtime, recently deprecated using Docker and moving to a different interoperability approach. So we'll talk about all that the next slides, but for now, let me set the landscape and define some terms. So first of all, the most basic or foundational part of the stack is a set of specifications. And the main specification here in this world of container management is OCI, Open Container Initiative specification. It describes how images are built, how containers should be run using those images, and how those images are distributed. So essentially talking about interoperable standard for registry API. Now, the next level is container runtimes and engines that implement this specification. And here, talking about container runtimes and engine, it's difficult to tell the difference. What's runtime, what's engine? We will use the word runtime in this presentation in very narrow sense. saying that run C is a runtime, for example, and everything higher level, container D is something between runtime and engines and Docker and Moby and Cryo, maybe considered engines and tool sets, Docker more than others. And again, so we'll talk about the differences. So we can just put them into the same category, call them container runtimes and engines. The next level is needed when we start talking about container orchestration and more specifically about Kubernetes. Kubernetes introduces CRI, which is another specification or interface that can be used to integrate container runtimes with Kubernetes. And the highest level is various tools that allow you to work with Kubernetes. With containers, images, using different runtimes and engines. And again, some of those tools, like Docker, for example, spans several categories. So Docker provides you with both container runtime and a bunch of tools. Others are maybe less prominent, like container D is mostly runtime and it only provides very basic tools. There are projects that only provide tools that can be used with various runtimes and engines. And again, we'll see that on a few examples later. And as tools, we'll look at things like Docker, CTR, this is basic container D tools, nerdctl, which is an independent open source project providing a CLI compatible Docker CLI compatible tools for container D. And then there are things like Podman and Builder. We'll also take a look at Bazel as a build system that provides a way to work with containers and images as well, although in sort of limited and niche fashion, which I'll explain. So let's talk a little bit about the specifications. So OCI, Open Container Initiative, consists of three different specifications. First of all, it's image specification, which describes essentially a format for image distribution files. So it explains how you can package image layers. It explains how you can combine image layers into a complete image together with the image manifest, etc., etc. OCI runtime specification describes container lifecycle, meaning essentially how containers are created, how they run, and how they should be stopped and deleted. Important note here is that OCI runtime specification doesn't talk about networking in containers. So it only talks about running containers as processes, and it relies on so-called hooks, which are part of this container runtime specification, so that tools implementing this container lifecycle can configure network for containers the way they consider correct. And in this area, another sort of standard was created. I'm not talking about this in this presentation, but just to make you aware. So called CNI, Container Network Interface. So there is a standard way to provide plugins for containers networking, and CNI compatible plugins allow you to integrate containers with pretty much any network environment out there. And the last part of OCI specifications is a distribution specification, which essentially describes a REST API for OCI image file distribution. Actually, the latest OCI distribution spec also allows you to distribute any other artifacts, not only images, which may be useful for applications. Now let's take a look at Docker and Containerd as a container as an OCI implementation, essentially. So if we look at the structure of Docker project, we'll see that at the very foundation of this project is there are two OCI implemented OCI reference implementation components, which are runc and libcontainer. So libcontainer is essentially a library that implements OCI runtime specification. So a reference implementation of OCI runtime spec. It's written in Go. It was written originally by Docker, if you remember this first slide when we looked at the history. So libcontainer was the first thing Docker separated as a component in its flow. It's written in Go. And used by Containerd for basic container operations. So another important component here is runc. So runc again is a binary which implements creation and running of container processes according to OCI runtime specification. Runc is a binary which uses libcontainer to do its job. And again, so this is relatively independent from both Docker and Containerd. It can be used by other container runtimes and tools, but rarely you would work with them directly. So they are deep inside of container runtimes and engines. The next level is actually Containerd, and Containerd is an implementation of basic container and image management tools. So Containerd runs a daemon, which listens on a socket and implements an API usually on a Unix socket on your machine. And your command line tools talk to that API and tell Containerd to do things with containers and images, like pull image from a registry or run a container or kill a container, etc., etc. So now the next level here is Moby. Moby, as we talked about that, is an open source upstream implementation, essentially maintained mostly by Docker, but also by a community of developers working in this area. So functionality-wise, Moby and Docker CE, let's say, are the same. And Docker, at last, is essentially a commercial implementation of container management tools based on Moby. Docker have their community edition, which is free for use. And then there is an enterprise edition, which includes commercial support and some additional advanced tools, etc., etc. So now, having looked at that, so hopefully we have a better understanding of the correspondence between these tools, and let's take a look at a different container implementation prior. So CRI-O was introduced by Red Hat. It's essentially an OCI implementation built from scratch, fully alternative implementation. And in terms of comparison with this stack, with Docker, Moby, Containerd, etc., it most closely corresponds to this level, to Containerd. So it's an OCI implementation providing basic container management tools. And what I mean by basic, we'll see when we work with a demo. But before going there, so let me talk a little bit about container orchestration. So now we come to this level where we need to orchestrate multiple containers on multiple nodes. Each node can run its own container engine, but container engines by themselves don't do much in terms of management of distributed systems of containers. So container engine is usually, not usually, but always focused on managing containers within a single machine. Now, some of you, if you're familiar with other tools provided by Docker, may ask, what about Docker Swarm? And in that sense, Docker Swarm, even though it's called or is considered a part of Docker toolset, so Docker Swarm is essentially a separate product built by Docker and packaged into the same set of tools, which provides container orchestration as well. So it's equivalent or corresponds to Kubernetes. So Kubernetes and Docker Swarm are on the same level of abstraction, do approximately the same things, but are just different implementations of the same concept. And Docker Swarm, again, orchestrates containers using Docker container engines running on each individual node. So going back to Kubernetes, and again, so probably this slide requires a little bit of explanation of how Kubernetes works. So Kubernetes consists of two main components, high-level components. On one hand, it's a Kubernetes master, a set of binaries, processes that run together usually and essentially store information about the cluster, the containers running in that cluster, and provide essentially orchestrating those containers. The other component is Kublr, which is a Kubernetes agent running on each Kubernetes worker node. And Kublr is responsible for making container do what Kubernetes requires them to do. So kubelets regularly talk to master, check to Kubernetes master, check which containers need to run.
Oleg? Sorry, I think the audio has gone out. still cannot hear you.
Can you hear me now?
Yes, we can hear you. Can
I'm
everybody
sorry.
else hear Oleg? Let's just
Yeah,
make sure everybody, yeah, it looks like it's working.
Yeah, I'm sorry. Sometimes looks like I had some issues with my USB or either new driver or something like that. And sometimes my mic just goes out. I need to switch to another mic and then back. So let me know if this happens again. Hopefully it won't.
Awesome. Okay. Thank you, Oleg.
Okay, so going back to our slide and kubelet managing containers. So kubelet does that using CRI interface, and there are several implementations. And historically, the first implementation is Docker shim. And of course, that originally was just an adapter inside of kubelet that allows kubelet to work with Docker. So it was just a package inside of kubelet code base that implemented Docker API and was able to run containers, sending commands to Docker API socket. Later, it was separated into essentially a separate component called Docker shim, which on one side implements CRI API, and the functionality stayed the same. Later, when kubelet implemented other support for other runtimes, mainly containerd, so another plugin was implemented directly as a part of kubelet when containerd support was introduced, called CRI containerd. Now this all is deprecated one way or another. So first of all, support for Docker and Docker shim goes away from Kubernetes in Kubernetes 1.25, I think, or 1.25 is going to be the last version which supports Docker using this Docker shim approach. Instead, it's recommended to use containerd directly. And the way containerd CRI adapter works also changed over time. So today, it's essentially a CRI plugin inside of containerd. Rather than a containerd adapter inside of kubelet, it became a separate CRI plugin, which is installed as a part of containerd. It's installed by default in most packages. So, and essentially, when you enable this CRI plugin in containerd configuration, you make containerd to open an API endpoint which supports CRI. And this is how kubelet works with containerd now. Cryo, on the other hand, another implementation of OCI container spec, implements CRI directly, and you can figure it from the name. So it was called as a reference implement. It was called Cryo because it was originally built as a, or invented as a essentially from scratch implementation of CRI API. So hopefully this clarifies a little bit correspondence between container orchestration tools and all those CRI, CRI, containerd, Docker, Docker shim, etc., terminology. Now let's see how all those tools work and where and how it looks from end user perspective, from a developer perspective. We'll start with Docker tools, with Docker, and we'll look at Docker as essentially this whole tool set stack for container management on a single machine. Now, to show that, I used Kublr. So this is our demo Kublr environment. I deployed a cluster called Container Runtimes here, deployed it in AWS. That's quite a small cluster, very simple. It includes 2 nodes, one master node and one worker node. And interesting detail about this cluster configuration is that I configured it in such a way that master is using Docker as its container runtime, while worker nodes use containerd as its container runtime. So this can be done in Kublr just by configuring some of the parameters inside of the cluster specification. So you can switch from Docker to containerd on one group of nodes or in the whole cluster. And this actually shows you that this modular approach, modular architecture works quite well. So Kubernetes as a whole doesn't really care what container runtime is used on this or that node. You can even mix and match. And this may be important, especially when you use some complex configurations, like if you run, for example, GPU nodes, you may know that GPU configuration and support for GPU on Kubernetes and in container management tools may require some careful and specially tuned configuration of your container runtime, so that you may be in a situation when, for example, you run a Kubernetes of the latest version but you still have to use Docker, for example, on your GPU nodes because Docker has a better support for GPU, or NVIDIA requires Docker runtime so that containers can work with GPU or something like that. And this ease of configuration and flexibility in terms of configuration is really important in those complex scenarios. Now we won't go into so many so complex areas. So what I did here in my command line, I actually used a kubectl plugin. So here I configured my kubectl. I use K as an alias for kubectl to work with this cluster. You can see there are 2 nodes, master and the worker. And I used kubectl plugin called node shell to actually log into each of these nodes. So the first window is where I log into master. And the second window is where I'm logged into worker. And I won't use them really as Kubernetes nodes per se. I will just use them to show you how working with Docker or containerd looks like. Because, as I said, the first one runs Docker, the second one runs containerd. And we'll start with the basic Docker commands. Well, not the basic Docker commands, but the first thing you need to do as a developer to run your application in a container environment, you need to build an image. And in Docker, the container image is described using so-called Docker file. So we can create a very simplistic Docker file. That here. So this Docker file is very simple. So the first statement here tells Docker that a new image that you want to build should use another image in the standard Docker image library called Docker Hub, called Alpine. So we'll use Alpine base image as a basis for our own image. And the only thing we will do to modify it is to add a wget package. So our image will be essentially an Alpine image with added wget package. So having created this Docker file, I can now build my image. And for that, I will use Docker image build command. I'm adding a tag argument, telling Docker that this new image should be tagged like this, my image v01. And dot here means that it should build the image using Docker file in the current directory. And this is done very quickly. And this is so quick because I already did that once. And you see Docker tries to be effective, efficient, and it uses cache. So it sees that I built the image already and no comments have changed in the Docker file. So it will just use a layer from the cache. It can play tricks with you from time to time, because like here, for example, the only thing I do with this image with my run command is to install a wget command. So, but what happens if the repository from where I install this command or this package was updated between my builds? So my second build won't be modified because this command doesn't really run again. So Docker just checks the command. But this is all intricacies, and you can tell Docker not to use cache with every build using command line options. So it's fully controlled by you. So you can decide what's the best strategy for you in each specific situation. Now, as a result of this command, I now have my image in local Docker repository or local Docker registry. And by the way, we see a bunch of other images here. This is because this is not just a node. This node is a part of our cluster provisioned by Kublr, Kubernetes cluster, and Kubernetes itself requires a number of images that it uses. So we see those images here. But we also see this newly built image with the tag we requested. So you can use Docker image commands to push images, to pull images from library, Docker Hub library. Like, let's say I want to pull another image. I can print Docker image pull command, say I want an Ubuntu base image now. So this is how it's done. You can see it reports that it pulled that Ubuntu image from a standard image library with the latest tag. And this is default behavior. I could also specify a specific tag. So image is pulled with a specific version. So next, we have our image built. Now we want to run a container, and running a container can also be done using Docker command. So we are using Docker run command for that. We specify the container name. If you omit this, Docker will invent some funny name for that container for you. And here I'm also specifying an I and T switches that essentially connect a terminal from that container to my terminal. And let me see what happens. That's because I already created that container before when I tested the environment. Let me remove it. Let's run our container. Okay, here we are. Container is now running, and my terminal, my console is connected to this container, and I can run commands inside of that container. We can check that inside of this container, it's very quiet. There is just one process, the root process, the shell that was started when I started this container. While if you remember that on the host where this container is running, on the actual node, there are dozens of processes are running right now because it's an active Kubernetes node. Okay, we can exit and we can check containers currently registered, and we see really a bunch of containers are really running there, busy with my Kubernetes node work. But we don't see our CNT1 container. Let's make it more visible. Here it. Why? Because this container is already stopped. When I exited shell, I stopped the root process of that container, and container was stopped. So I need to augment this command, and I need to run docker ps-a, which also shows stopped containers. And now at last we see our container, which is in stopped status, and reports to us that it was exited a minute ago. I can run container as a demo. Let me try that. And again, we see that this container exists. It cannot create another container with the same name, so I will need to remove. And now I can create a container using a little bit different command. So I give it the same name. Now instead of -it, which makes it interactive, I give it -d daemon switch, which makes this container disconnect from the terminal immediately and return the control, and the container stays in the background. The only other difference is that here I specify the sleep 1000 command. This is because if I didn't, it would just run the shell in the container, and the shell would immediately exit, and the container would be stopped again. But now we have a process which is actually sleeping, running inside of that container. So we can run docker ps without -a option. See if our container is there. Yes, it's there. It's running for a minute, and it shows us current process running in that container. Now we can again stop that container or kill it, and the difference is actually similar to the difference in the way you can stop a Linux process. You can send a SIGINT signal to it, which is graceful shutdown, so to say. So process can use various hooks to gracefully complete. And if it doesn't work, you can send a kill signal to a process, which is unconditional, dirty kill of the process. In our case, we don't have important data there, so I can easily use kill command. Usually it works faster. So this is the basics of Docker command line. So you can work with images, implementation of image spec. You can work with container implementation of OCI runtime spec, and you can push and pull images to image repositories, which is implementation of container distribution spec, OCI distribution spec. Now let's take a look at a different implementation, containerd. And for that, I'll go to another node, which is running with containerd. Check that Docker indeed is not available here, is not installed. But fortunately, containerd provides its own tools. We'll also talk about a few different differences in containerd, and one of the most important differences with containerd is that it doesn't use Docker Hub as a default container registry. So you would have to always specify container registry when you work with containers. Another important difference is that containerd provides you with namespaces. So if we run ctr namespaces list, you will see that here we have two namespaces, Kubernetes.io and my namespace. My namespace is a namespace that I have just created, checking this environment. It's easy to create a namespace. So here I created another namespace, and namespace separates different areas and different sets of images and containers you work with. So now you can use CTR commands, pull to pull an image. You always have to specify namespace now, unlike with Docker. And here I pulled an image. I had to specify full image path with Docker.io, but now it's here in my local repository. And now I can use container commands, CRD, that let me check, for example, which containers are currently running. I don't have any running containers. I can create a container. Now I have my container here, but I don't have it running yet. So it's again another difference with Docker. So to run a container, you need to actually create a task which starts this container I have just created. And only now I got my container to run, and it executed this command echo hi. So I see the output. So you can see the list of running tasks. Again, now I don't have any running tasks because my container task is just completed. I can just as well clean up my workspace, my namespace, remove my container I have just read. So you can see the difference already. So container D provides tools that are much lower level than Docker's. So container D doesn't provide build images, for example, and doesn't provide network setup primitives. So whenever you create a container, you have to configure network by yourself or using other tools. So it's essentially a more basic level tool than Docker. Interestingly, containerd, we talked already that containerd is a part of Docker. We can check it in our Docker node. If we run CTR tool here on the Docker node, we will see that it works. We indeed have a containerd installed here, and we even have a namespace named Moby there. So Moby is essentially a namespace which Docker creates under the hood and which Docker uses to host its images, its containers, etc., etc. Okay, as far as it's clear, getting that out of the way, we can talk about a few other tools like Nerdcuttle, for example. Nerdcuttle is an open source tool, an attempt to provide a drop-in replacement for Docker in a containerd environment. So Nerdcuttle has a benefit of being a simple binary, which you can just download and run. And provides all the similar commands like image list, for example, and it will just translate them into containerd API calls, and it will give you an output looking very familiar to how Docker works. Cons of these tools are that it doesn't yet cover everything that Docker covers. So for network, it depends on CNI. You have to install and configure CNI plugins for Nerdcuttle to be able to configure network. It depends on Moby build kit D. This is another component of Docker for image build commands to work. So essentially, it has its benefits, it is not suitable for all use cases, or at least you have to configure it additionally. Another attempt at replacing Docker is Podman and Builder. So this is a combination of tools. Podman uses Builder under the hood, and Podman provides more complete, essentially, drop-in replacement for Docker, to a degree that in latest CentOS and RHEL images, Unix images, or Linux images, Red Hat provides Podman package instead of Docker. So essentially, RHEL includes containerd, Podman, builder, and an alias. So when you run Docker command, it is under the hood runs actually a Podman binary. That is convenient for developers for command line work, but for some advanced use cases, this may suddenly uncover some incompatibilities between Podman and Docker. So beware of situations like that. And the last note I wanted to mention Bazel as a tool to build images. Unfortunately, we don't have much time left for that. So I'll just say that Bazel, being a general purpose build tool, as a part of its plugin base, provides a set of tools to build container images. And the benefit of Bazel is that it can build container images completely without the need for Docker or containerd or any other container image installed. The con side of this coin is that you would require to completely rework your Docker files, and it's a little bit more complicated. It requires a little bit more planning. But again, another benefit is that your build, your image builds can be then completely hermetic, repeatable. So you would get predictable results when you build your images, which is not the case with other ways of building images. And so here now you can see that the situation with container management tools is really asymmetric. So different tools provide different support for different aspects of container management processes. And I hope that this presentation gives some idea of where those tools are comparable, where they are not, where and how you can combine, mix and match, etc., etc. So we provided a bunch of links here that will help you go further and dig deeper into this topic. And now I think, so yeah, there are some areas which we did not cover, of course. It requires a lot more time. Things like Docker Swarm, things like various Docker registries, Artifactory, etc., etc. Things like Docker Notary is a very interesting tool in Docker that allows you to sign images and make sure that the images are unmodified. Windows containers have their own specifics, etc., etc. So again, here I would suggest to take a look at those capabilities. But now, hopefully, you will at least be aware of these areas of expansion. And now we are open to questions.
So we do have a question with a preface. So as you were showing, Oleg, Docker Engine uses containerd in the background to talk to, excuse me, I'm so sorry. And you can also see this in the comment section, Oleg. But his question is, could a direct interaction with containerd on a Docker node have unintended side effects?
Yes, I think it could, but so probably not. So essentially, what happens under the hood when Docker works with containerd, it uses containerd to manage images and containers, and it uses its own namespace. So if you use a separate namespace, you won't break anything for Docker. If you get into Docker's Mobi namespace and remove something there. Here, I don't know. It may have unintended consequences. Docker may have its own separate meta information about those containers. I would expect, though, that it's written using all the best practices, and it would garbage collect anything that is unexpected. But I wouldn't rely on that behavior. But if you use your own namespace, I think it's not going to be a problem. The question can be expanded, though, to Kubernetes. So is it a problem if you use Docker engine or container engine running on a node, which is also used by Kubernetes? And here the question is a bit more complicated, mainly because of resource management. So when Kubernetes creates a container, it uses various meta information provided in the pod definition, including resource requests and limits. And when it works with its own containers, it can account for resources and limits used by containers created by Kubernetes. When someone starts containers going around Kubernetes API, so Kubernetes just doesn't know that those resources are used by those additional containers, and it can lead to various problems like OMTs, etc., etc. But other than that, I don't think there is going to be any interaction.
Okay. Thank you, Oleg. And to respect your time, we are going to wrap things up. We do want to say thank you so much for joining today's webinar. Please feel free to reach out with any questions or topic suggestions, and we hope that you can join us next time. Thank you.
Thank you.